So in this research log, I will be talking about concepts that pertain to nuclear chemistry, unlike my previous research log, which talked about concepts that pertain to quantum physics. So let's get started. Alright, so the two biggest concepts in nuclear chemistry are, well, as you probably know, fission and fusion. So what are they? Well, fission is, when a nucleus splits apart, and fusion is when it fuses together. And so both release a lot of energy, and this energy can be harnessed for power. But there's a slight problem with both of them. Well, not really a slight problem, that's a very subjective view, but the problem with fusion is that it requires a lot of energy, and really, more than energy, is the heat needed to fuse these nuclei together is around 5 million degrees Kelvin. So the common fusion reaction is deuterium plus some more deuterium at a very high temperature is converted to tritium, and a neutron occurs as a product, plus a lot of energy, usually 3.27 megavolts. So this is a lot of energy, but it requires a lot of heat to get to this state. So now let's talk about fission. Fission, well, first of all, it's very infamous for some of the nuclear disasters that have occurred over the years, such as Chernobyl. But another big problem is the nuclear waste that's created after. Because fission can be contained to an extent where it is safe to use it for energy, but the problem is that there's so much nuclear waste that can be radioactive for millions of years, and so eventually this nuclear waste will leak into groundwater, and this would be very dangerous for human consumption then. And so, well, let's look at the products of fission, and then we can see where we can go from there. So the common products of fission are 93.4% uranium and 1.27% plutonium, 0.14% of other actinides, and 5.15% of just other fission products. So this is what we're looking at right here. So where is the other about 0.7%? That is in enrichment. Because the component that is most largely taken in is uranium. It's taken in at about 100%. So what happens? What is the enrichment of uranium? Well, that is actually quite a big concept, and so enrichment is the ratio of different isotopes of uranium. So hopefully you guys know that nucleus of an atom is composed of protons and neutrons. So different isotopes of different elements are just how many neutrons can be in the nucleus. Eventually, when you have too many neutrons, then fission occurs. And so when fission occurs, then you can harness that energy. And so what we want is fission occurring at the lowest possible energy intake. And so how do we get this to occur? The most efficient atom that can be taken in for this is uranium. And so this is the atomic symbol for that. And so the thing about uranium is that it comes in two isotopes, really. And that is 238 and 235 being the atomic weight. So these are just commonly known as U-230 and U-235. So what we want is the right amount of U-235, but the mixture of U-235 and U-238 really messes up the whole fission process. So how do we get it so that we can separate the U-235 from the U-238, because these are usually just mixed together, and then we can put it back into U-238 in the right ratio. So that is really the process of uranium enrichment. So there are three main types of uranium enrichment, and they are gaseous, diffusion, centrifugal, and laser, which is the more common type, or the most recent type actually, and the cheapest type. So gaseous diffusion is when you have a chamber sort of like this. And so what happens is you have your mixture going in of both U-235 and U-238, and there are little pores in the wall right here for the pipe. This is the pipe. And so the U-235 is actually smaller because of the lower amount of neutrons that it has. So the U-235 diffuses through here. And so eventually, if you do this many times, possibly thousands of times, you finally get the U-235 out of the U-238. And so that's how gaseous diffusion works. And it's not so efficient, but it does work. So then you have the centrifugal separation, where you have a chamber sort of like that. So all the U-235 and U-238 are right here. This is actually a circular chamber. You can go around here behind that. This is sort of a turny thingy. I don't know really how else you could describe that. Maybe a fan. But what it does is it turns, and so the lighter, less dense U-235 goes towards the center when this starts spinning. And the U-238 kind of starts lying around the outside. And so, again, with a lot of centrifuges, you can eventually collect all the U-235 from what has traveled from the lowest, to the region where the lowest densities of uranium would be present. So now we're talking about laser diffusion, which is actually the most efficient way of doing it. And earlier this year, there was sort of a crisis with Iran possessing nuclear weapons. Due to Iran's nuclear knowledge on this type of enrichment, they were actually able to acquire these weapons. Without laser enrichment, Iran wouldn't have these weapons. So this is a very controversial thing in the US. But I'll still describe it to you. It's since Iran knows it now. Almost everyone really knows it. So you have your U-235, U-238 here. And so pretty strong laser is shot through. And so what occurs is, since U-235 it's the more unstable of the two. It's the more unstable isotope, so it's more likely for fission to occur with U-235. So since it's more unstable, its electron shells are also more unstable. And therefore, it ionizes more easily. And because it ionizes more easily, you are able to magnetize the U-235, and then you can put a magnet down here and all the U-235 will come in. But it takes more ionization energy to ionize U-238, and therefore it won't come towards the magnet. So that's quite a nice concept, really, and it helps out. But after some research, I feel like I've discovered an even cheaper way to do this, and this is where my personal research comes in. So there's this process in quantum physics, which now I'm going back into, called quantum tunneling. So as you all probably know by now, well, particles such as electrons act really weird in the quantum world. So let's say they're in a box. So they're not just particles. Let's just say we're talking about one particle. It's not just in one place. It has a likelihood of being in all these places. So it's kind of like a wave, really. And has an even likelihood of really being anywhere inside the box. So it's not really a wavy wave in the box. It's just sort of a straight line. And so these are the walls of the box. And so now there's a very low probability, but there still is a probability that this electron could be in the walls. And then there's a probability that it could be out here too, outside the box. So this is known as quantum tunneling, where this electron, it could be in here, anywhere in the box, or it could be out here, somewhere out here. So that's the thing about quantum physics. It's both a particle and a wave. So the thing about quantum tunneling is the closer two particles get together, the more likely they are to quantum tunnel. So the more likely the electrons in them really are. So let's say you have these two atoms, and they're not so likely to quantum tunnel. But the closer they get together, exponentially is how fast the growth rate of quantum tunneling is. Like, from here, if the nuclei traveled, or if the atoms traveled to right here, the quantum tunneling rate would increase by probably about 1,000,000 or 1,000,000,000,000. So they're way more likely to quantum tunnel. So my idea is, let's say you have these 4 uranium atoms. And so what you do is you apply pressure to the center spot so that the uranium atoms come rushing in. And so then all you're doing is applying pressure here. Notice that you're not shooting any sort of laser, which would actually cost a lot of money, but all you're doing is applying pressure there. And so you apply just enough pressure that the U-235 come really close, but not the U-238. You apply just enough pressure that the U-238 just kind of remains out here, and the U-235, it's still in the mixture, but since it's more unstable, it's more likely to ionize. And since it's more likely to ionize, it will ionize, because quantum tunneling will occur if they get close enough. If you apply enough pressure, quantum tunneling will occur. And that'll cause electrons to go from place to place, escape from their shells. And so, therefore, it'll be ionized, and you can use a magnet again to take the U-235 out of the mixture. So what I'm saying is, since U-235 is more likely to ionize, it therefore is more likely to quantum tunnel, because the electron shells are much more unstable. So we can use this property of uranium-235 to make it much easier to enrich uranium. And this would make nuclear weapons way more easily accessible. But it would also reduce nuclear waste, and therefore make fission a more feasible and viable process for not only the US, but countries all around the world to use. So this is what my research has been on for the past month. But of course, I will research further into this field and see if there are any other solutions to the nuclear enrichment problem.